I have the great privilege and responsibility of directing a laboratory at HP Labs, which we call the Information and Quantum Systems Laboratory. Within this laboratory, we're actually working on three major areas right now. One is sensor networks, one is photonic interconnect, and the third is something called the memristor. After thinking about this invitation to come here and give a talk, I realized that everyone in this room would know more than me about sensor networks and photonic interconnect. And so in order to avoid looking stupid, I figured I would talk about the one thing that I might actually know more than you folks do. And hopefully you will at least find it somewhat entertaining. Many of you will actually wind up thinking that it was all science fiction in the end, but we'll see where we go. What I'd like to say is that the work that I'm going to be talking about essentially has been going on since about 1997. And if I count up all of the people who have contributed in one way or another to this work, people from HP Labs, and from our academic collaborators over the years, it's probably exceeded 200 people. So to try to summarize all that work in 45 minutes is challenging at best. So what I'm going to do is I'm going to concentrate on the work of a few people who are listed on the right-hand column here. In fact, the bottom four people on the right-hand column are all postdocs who are now looking for academic positions. So we'll see where that's going. So what I'm going to talk about today is actually mostly about the memristor itself. If you haven't heard about that, it's a device. And so my background is in physics and material science. And so I'm going to talk a little bit, but hopefully not too much detail, about device physics and the materials. And then sort of wave my hands and talk about some of the applications of this device. I have some help, and I have some helpers in the audience here. So Jeff Mogul contributed a few view graphs to this stack, which I barely understand at all. So if there's questions along those lines about systems issues, then Jeff will be kindly making himself available to answer systems issues. So first of all, what the heck is a memristor anyway? Well, the memristor is actually the fourth fundamental passive circuit element. Now, for about 200 years, we've known about three passive circuit elements: the resistor, the capacitor, and the inductor. These were discovered essentially, as I said, the most recent one about 180 years ago. And so all of the electronics that we have built in that time has really been based upon these three passive devices. And then, of course, most recently, the transistor. But the transistor is not a fundamental circuit element. You can write an equivalent circuit, the Thevenin or Norton equivalent circuit, for a transistor, which just has a source of energy and essentially resistors as part of it. So the wild sort of thing that happened was that in the 1960s, there is this crazy guy at UC Berkeley named Leon Chua. Now, I don't know how many of you people have ever heard of him before, but in fact, Leon Chua is to circuit theory what Albert Einstein was to relativity. In the 1960s, Leon Chua, who was probably more of a mathematician than anything else, was the first person to put nonlinear circuit theory on a firm mathematical foundation. He essentially writes his papers as a series of proofs, and so perhaps unfortunately, very few people actually understand what he has accomplished. But it's a magnificent accomplishment. He is known as the father of nonlinear circuit theory. And the issue is that even though he has all of these elegant mathematical proofs of essentially how to understand if a circuit is essentially going to work or not, his work is practically unused even today. People literally just design their circuits by the seat of the pants, simulate them with SPICE, and if they don't work, then they go and fiddle around and do something. So there's nothing provable in what a lot of people do today about their circuits. But Leon essentially showed how to put things on a mathematically provable basis. Now, as he was doing this, he noticed that in his nonlinear circuit theory, there was something missing. And this is akin to what P.A.M. Dirac did in the 1920s when he generalized quantum mechanics with relativity, and he noticed that there was something missing in his equations, and so he was able to predict a particle called the positron. Well, Leon noticed that there was something missing from the circuit equations. And without getting into too much detail, what I can just show you here is this little diagram. And if you think about the four fundamental issues that you try to think about in circuits, the voltage, the charge, the current, and the flux, there are 6 equations or 6 ways of relating those 4 things, but there are only 3 fundamental passive devices. And so what Leon postulated was, based essentially on symmetry and beauty, if you will, there should be a 4th fundamental circuit element, and he wrote down the equations describing that circuit element, and he wound up naming it the memristor. And the reason he called it a memristor is because it is essentially a resistor with memory. And so you can see the circuit diagram, or the element diagram that he invented. It sort of looks like a resistor, but it's changed a little bit. And in some sense, the memristor exists in order to relate the flux in a circuit to the charge. Now that's very unusual, very sort of puzzling. And in fact, he published his original paper in 1971. And there was a flurry of activity of people trying to find the memristor, because the title of his paper was Memristor, the Missing Circuit Element. And in the paper itself, he essentially says, well, here is a mathematical proof that if such an element exists, it's a fundamental circuit element, and it essentially completes or makes a complete set of the known circuit elements. But people just simply couldn't figure out what physics could give rise to a coupling between flux and charge in a circuit. Well, it turns out, I think, that in part there was a real problem here in that people were looking for causality. And in fact, in this equation, there's nothing that says something has to cause something. It just says the two things are equal. And so any physical interaction that makes this equation true essentially gives rise to a memristor. And that's effectively what happened in my laboratory. We figured out a cheat, if you will, in order to make this equation true. And I'll talk about that in a little bit. But it turns out that this simple memristor equation, which relates the flux to the charge, is almost a red herring. I mean, I think it really did confuse people for a long time, and it put people on the wrong path. A few years later, what Leon did, he and a former graduate student of his, Steve Kang, who is actually now the chancellor of University of California at Merced, realized that the important issue of the memristor is it was a passive device with state. In other words, there is a memory within the memristor, and that memory essentially is represented by one or more state variables for the device. And so, in fact, if you really want to characterize a memristor, you can't use only one equation. A memristor actually requires 2 equations to characterize it completely, and I write them here. One equation essentially states that there is a quasi-static conductance relation between voltage and current, but the resistance in that equation depends upon the state of the device at any given point in time. Then there is another equation, which essentially is a time-dependent equation, which tells you how the state variable evolves in time. And so you actually need both of these equations in order to be able to put a model for the memristor, for instance, into a SPICE simulation to make any sense of it. And if you'll notice that these 2 equations don't say anything about flux. Okay? So in fact, if there's some way of having a device that has this state issue that evolves in time, you can have a memristor. Now, those 2 equations essentially predict that the memristor itself should have an IV curve, which looks like that little diagram up at top. You can see that it looks like a figure 8 or a bow tie. That's what we used to call it in my lab. Leon Chua called it a pinched hysteresis loop. And in his 1976 paper, he essentially just stated that if you see a pinched hysteresis loop in an IV curve, you've probably got a memristor. Now, what makes the memristor fundamental? Why can we claim that it's fundamental? Well, if you look at that pinched hysteresis loop down in the lower right, it turns out that I challenge anyone to figure out how to make a circuit using only resistors, capacitors, and inductors, and you can make those devices as nonlinear as you wish to come up with the IV characteristic of the memristor. It can't be done. In fact, Leon showed that, proved it mathematically. That's one of the major reasons why it really does belong to the pantheon, if you will, of the fundamental devices. And when I'm talking about fundamental devices here, when I say resistor, I'm not talking strictly about a linear device. I'm including such things as diodes and tunnel junctions and anything else that has an IV characteristic without a hysteresis loop in it. So that's essentially where Leon was able to take this, and then for practically 40 years it just sort of disappeared out of people's consciousnesses. However, it turns out that even before Leon published his first paper, there were people who were publishing papers in the literature which were showing pinched hysteresis loops. And so here are just a few of them. In fact, there was a paper written in 1970, a review article on all of the work that had been done in the past year where people were seeing these funny pinched hysteresis loops. And the problem is that people just didn't know what it was. And so if you look at the titles of those papers, usually it says something like anomalous capacitance or something this or something that, something strange is going on. Well, the fact is that the something strange that was going on is all these people were making memristors and they simply didn't know it because they didn't know what a memristor was or how to characterize it. They didn't understand that these are dynamical devices and you actually needed two equations to characterize the device. So they were trying to shoehorn these devices into a model which only included resistors, capacitors, and inductors, and that's impossible. Okay? So literally, there's been hundreds of papers published about this over the years, and it was just quite a muddle. And what's sort of interesting is that none of these people ever stumbled across Leon's paper, and somehow he didn't read any of theirs. Well, I mean, in part, that's almost understandable. The guy's a mathematician. He doesn't read experimentalist papers. So, how did we essentially find the missing memristor? Well, I had been mucking around with this stuff for quite a few years, and finally I just got sick and tired of wondering what was going on. And so in August of 2006, I essentially sat down and I swore to myself that I was going to figure this thing out. And on the 26th, I finally did. And so the idea behind the memristor is, here is a particular type of device that we have been making in my lab for years, and long before we ever knew what a memristor was, but it was a simple device with two platinum electrodes on either side and a thin film of titanium dioxide in the middle. Now, titanium dioxide is many different things. Depending upon who you are, you can think of it as a mineral, a ceramic, or whatever, but it's also a semiconductor. It's a wide band gap semiconductor, and the other interesting thing about it is that it is auto-doped. In other words, if I take out a little bit of oxygen from the titanium dioxide, that's essentially N-type doping the material. And the oxygen vacancies that are left inside the material are essentially positively charged, effectively positively charged. Now, those vacancies are slightly mobile, very slightly mobile. But if you essentially put a large electric field on these things, put a positive voltage on the right-hand side here, it's actually conceivable anyway that you can take those vacancies and you can push them toward the left in the device. Now, what does that do? Well, what that does is it makes the white part there that I'm labeling TiO2, the stoichiometric material, which is wide band gap semiconductor, it makes it thinner. And so that should reduce or lower the resistance of the system. If I then flip the voltage, I can pull the oxygen vacancies back the other way, and that will cause the resistance of the system to increase. So at least in principle, here is a device that we can switch by using voltages in a way that actually gives a pinched hysteresis loop. Now, I would say that the breakthrough, the one thing that I did to essentially understand what was going on here was I essentially wrote down a simple equivalent circuit of this device. All right, and this is essentially the extent of my abilities in electrical engineering. I can't write down a circuit diagram any more complex than this. And so what I have here is essentially two variable resistors in series with each other. One variable resistor essentially representing the titanium dioxide when it is stoichiometric, and the other one when it has oxygen vacancies in it. And the idea being, if I can push or pull a dividing line, or the end state between the oxygen vacancies and the stoichiometric part, I essentially can vary the resistance of the total device. So then I was able to write down two equations. I was able to write down an equation for the electronic current, which essentially showed the voltage is a function of the current and a resistance which depends upon a state variable. And what's the state variable? The state variable is the position of the dividing line between the doped and the undoped material of the system. And then I was able to write down another equation, which is essentially the dynamical state equation of the device. And what this says is that the velocity of this dividing line, and that's called drift, right? So you study about drift in devices. So the drift is equal to essentially the electric field times the current through the device. And I just write the electric field in this form here, showing that it's actually proportional to the current. Well, those two equations are exactly the equations that Leon Chua wrote down to define the memristor in the first place. And so this system, if it actually exists, is a memristor. Now, the other interesting thing that came out of this is I was able to take those two equations and I was able to write down an equation for the memristance. And here is the interesting issue that came out of that. You see that the memristance in this very simple model where I have linear conduction and linear drift turns out to have a term which is inversely proportional to the width of the device, 1 over d squared. What that means is that memristance is 1 million times more important at the nanometer scale than it is at the micron scale. And at the millimeter scale, it's completely unobservable. Now, that actually winds up coming back and allowing us to understand a huge amount of literature that is out there, because a lot of people have been building nanoscale circuits or circuits with nanoscale devices in them, and they are reporting all sorts of strange hysteresis effects in their circuits. And so what they're doing is they're looking for some source of inductance, they're looking for some capacitance that they don't understand. Well, guess what? What these people are seeing is memristance. At very high fields, which you get by having even voltages of 1 or 2 volts, but dimensions of a few nanometers, those fields are large enough to cause atoms to move. And one way of thinking about memristance is it's the coupled motion of atoms and electrons in a device. So anytime you get that, you've got memristance. And so people essentially have found or discovered memristance, again, all over the place. There's literally hundreds of papers in the literature that have been published in the past few years where people are screaming like crazy talking about anomalous inductance or capacitance in their circuits. It's not anomalous inductance or capacitance. People are finding memristance all over the place. It's a fundamental circuit element. So what do we do about that? Well, why don't we take advantage of it? Can we actually use or build memristors to do something interesting? Now, one of the issues that first came up is if you start thinking about drift and diffusion of species in a system, there's something called the Einstein-Nernst relationship, which tells you that if I have drift and diffusion together, the speed or the velocity of diffusion is only about 3 orders of magnitude lower than the speed of drift. You just sort of write that down and plug in reasonable numbers, and that's what you'll find. And what that means is that in a memristor, trying to use it as a switch, if I'm able to switch the device really fast, its lifetime is very short, Or if I want a long lifetime, it would take a very long time to switch it. That doesn't seem to be very interesting, but it turns out that there's a little piece of physics that comes to the rescue here, and that is something that's been known since 1940 from Neville Mott, actually, who showed that in very, very high fields, the drift velocity is actually exponentially dependent upon the field. And in fact, that exponential can be huge. You can have 20 orders of magnitude of change in drift velocity as you vary the field by a small amount as you get into this very high field regime. So at the nanometer scale, with a couple of volts on your system, it turns out that you can get into a regime where the field is lower than the dielectric breakdown field of the material, but high enough to get things to drift really fast. In fact, we've measured drift velocities in our devices of 1 meter per second. That's enough to be able to take a device and switch it in a nanosecond. But after we turn the voltage off, or if we stress these things and look at lifetimes, our aging results essentially diverge. It predicts an infinite lifetime. And in fact, that's even known from geology. So that's an interesting issue. I mean, we have here devices that, at least in theory and in experiment, can be switched extremely fast, but have very, very long lifetimes, essentially geological time frames. So with that in mind, we essentially decided that what we had to do was make measurements of these devices using an appropriate set of experiments in order to be able to characterize both this quasi-static conduction mechanism of the device and the dynamical evolution of the state variable. And what that means is you cannot plug these devices into a parameter analyzer. In fact, if you do plug one of these devices into a parameter analyzer, depending upon how new it is, it will drive it crazy. You'll actually get you can see all sorts of papers, and we see them all the time. We can actually tell you what parameter analyzer people were using to try to characterize their devices. Because what happens, of course, is that modern parameter analyzers have all sorts of software in them to try to signal average and give you a beautiful IV characteristic or beta of a transistor. Well, for a dynamical device, if you're trying to signal average, the device is changing in real time. So you can actually get into a positive feedback loop where these devices actually drive the parameter analyzer into oscillations. And so people actually publish this all the time and talk about all of these interesting oscillations that they're seeing. And what it is, in fact, is that they don't understand that it's just the software in their parameter analyzers that's being fooled by the device. So what we had to do is we've had to build all of our own systems for characterizing these devices. And we have to do it in a two-step process. So first what we do is we do a series of measurements where we look at the state of the device. In other words, we collect an IV curve over a very small range, and so we can look at the quasi-static conduction of the device, and then we give it a pulse. And here I'm showing you a pulse of 1 volt, and what that pulse does is it causes the state of the device to evolve. Then we characterize it, pulse it, characterize it, look at it, and since these things have this exponential dependence, our pulses actually increase exponentially in time. So that we can actually look at these devices over many orders of magnitude of time. In fact, in this particular example here, we start with a 1 microsecond pulse, and at the end, the total integrated time under voltage is about 33 seconds. Now, then what we do is we reset the device back to its initial state, and then we do another set of probe and pulsing experiments at a different voltage. And then we have to turn it back and do it at a different voltage, turn it back and do it at a different voltage. So you have to essentially wind up doing thousands of measurements, unfortunately, but of course, if you've got it all programmed up, you just punch a button and it can all be done automatically. And what do you get in the end? Well, you wind up getting about 1,000 IV curves, and those IV curves essentially can be arranged as a function of both time and voltage. Voltage history, switching voltage history. And so that's shown on the right-hand side there, some small number of IV curves. And what we do is we fit those IV curves to some reasonable equations which would describe the conduction of the system. Now, for the particular devices here, it turns out that the conduction fits extremely well the Simmons theory for tunneling. And so what we can wind up doing by doing all of these fits, we can do essentially iterative types of fits, and we can determine the width of the tunnel barrier in the device as a function of time for different voltages that we obtain. All right? So here I'm showing you essentially what's the quasi-static conduction equation as a function of some parameter, W, where W turns out to be the width of a tunnel barrier in the device. And now here what we can do is we can plot this width, the state variable, or the tunnel barrier width, as a function of time over 6 or 7 orders of magnitude here for both switching of the device off and for it switching on. And then with these essentially plots here, we can write down from some, approximations that we make, analytical formulae for the time dependence of the state variable, or the time dependence of the width of the tunnel barrier. These equations here, along with the Simmons tunneling equation, essentially represent something that you can put in a SPICE model and simulate the devices. If you have this W dot function here, you can know everything that there is to know about the device, about all of its dynamical behavior. So you can calculate how fast you can switch the device, how long the device will live. It turns out that we know from this that you can switch the device in nanoseconds, and we've done that. And the equation itself diverges at long times, which says that it effectively has an infinite lifetime. The state has an infinite lifetime. So that's where we are with this. It also turns out that our electrical characterizations allow us to understand something about the inside of the device. It turns out that devices that have been made for the past 40 years have always undergone some sort of what people call a forming process. You've essentially got to zap it with a bit of a voltage first to actually get it to start switching. And people didn't understand what was going on there. Well, we actually came up with a model of what was going on. The zapping or the forming process essentially creates vacancies in the first place in order to get this thing to start going. And then once you've essentially electroformed it, then you can go off and start switching, although the electroforming process is a little bit ragged. So we predicted that there should be a filament essentially inside the device, and from the tunneling equations we could even say how big it was. So we then actually took a device and pulled it apart, and there's the filament. You can see it right here. So the diameter of this thing is about 100 nanometers. If you start off with a device that's several microns on a side, we then actually started building devices on very, very thin membranes so we could look inside of living devices. So we've actually built memristors now where we can then put the memristor in a transmission electron microscope or in a X-ray beamline at Berkeley and look inside the device as we're switching it or as we're forming it. And so we've done that, and here's a TEM image of the little filament area, and we can actually identify the chemical form of the switching material, and it turns out to be a compound, a thermodynamically stable compound called TI-407. And one way of thinking about TI-407 is that it is a condensed phase of vacancies in TiO2. So once we got to this point, we no longer have to form our devices because now we actually build our devices intentionally by depositing a layer of TI-407 to be a source or sink of vacancies, and then a thin layer of TiO2 on top of that. And so that's essentially what our devices look like now. So we get this very large source or sink of vacancies that we can push and pull and into this area here. So how am I doing on time? Without a
15 minutes.
Okay. So I got. So now let's talk about some applications, or some possible applications of this. So we actually have now built within Hewlett-Packard hybrid transistor or hybrid CMOS memristor chips. All right. So what we did, we had to essentially using a fab that was actually made for inkjet cartridge chips. We fabricated essentially a CMOS system, which was meant to effectively be an emulator of an FPGA. And so what we were then able to do was on top of the CMOS, we were able to come in and put our memristors. And so in this fashion, we're able to show that memristor fabrication is compatible with CMOS fabrication. But then we're actually able to use the transistors to switch the memristors from one state to another. But then once they've switched, we can use them literally as connections within a CMOS circuit. And so here we've got this system which is an FPGA-like system with memristors essentially pulled out of the plane, or the switches, if you will, the configuration bits, and all of the wiring and switching pulled out of the plane of the CMOS and put into a layer of the metallization. And so, you know, at one level, you know, this is sort of a proof of principles for doing that, but we think that we can actually use this to build FPGA chips that have 10 times the effective logic density of today's FPGA chips, because actually most of the area on an FPGA now is the configuration bit and the wiring. It's not the logic itself. So by lifting that out of the plane of the CMOS, we can condense all of the logic into a much smaller area, so we can get 10 times the density of logic on a chip with essentially a big increase in both the speed of operation of the device and a large decrease in the power dissipation. So that's one of the issues that we're working on here. Since the physics probably doesn't interest you all that much, I'll just say that it's all about, it's a semiconductor device in which atoms and electrons and holes are all moving simultaneously. And if you keep track of it all properly, and you understand that you're only moving the vacancies or the dopants in the system about a half a nanometer, and that gives you a switching ratio of about 1,000 to 1 in the device, that's where you're going. So what does all this mean for systems people? So this is, you know, if you have questions here, I have a volunteer to help me out here. But, I mean, look, we've been, systems people have been looking at this trade-off now between DRAM, flash, and hard disks for a long time. And how do you balance this? I mean, where is the, I mean, can you put flash and sort of in between DRAM and disk as a buffer? Or, what are the trade-offs that you try to deal with? Of course, DRAM is, you know about it. It's fast. It's relatively low power, but it's volatile. Disks, disks today are like a reservoir that you've got to suck through a straw in order to be able to get data into and out of that reservoir. And things are only going to get worse. I mean, DRAM, the end of the DRAM roadmap is probably within 3 years. So we don't think that DRAM is going to scale at all beyond 3 years from now, and that the only way of doing, increasing effective DRAM density is in stacking, and that's a real loser in terms of power and heat. Flash cells also, we think, are the end of scaling for flash is essentially already here, and the only way to improve that is to increase the number of bits per cell, and you do that and you dramatically decrease the reliability and the endurance. And disk, I mean, who knows where the disk roadmap is, but I personally don't think it's going to go on for very much longer. Well, the memristor is very interesting because it has power and speed of a DRAM cell, but it has the lifetime of a bit of a hard disk. Now, right now, one of the problems that we have is that the endurance of our current memristors isn't much better than flash, but it is better. So this is something that we're looking at. So we're trying to figure out where memristors are going to fit in all this hierarchy and what sort of impact that we're going to have on computer systems. But, sitting where I am and being pretty optimistic, I believe that memristors at some point in time, and I think it could be as soon as 5 years from now, could literally completely replace both DRAM and hard disk, and maybe even eventually CDs and DVDs. So this is a pretty interesting issue. So some of the challenges. So we've got this new class of device, but it's got very, very different properties. I mean, this is not something that you can just plug in and replace your DRAM with. So you're going to have all sorts of issues with respect to standards and protocols. How do you deal with issues such as your memory controller, the sort of physical address bits, and all of the other trade-offs that you do, and when does it become economically essential to do that? Because that's, you know what this industry is like. Nobody ever does anything until the gun is there and it's cocked and it's about ready to go off, right? And so there's going to be a point where you can tell that economically it's not just nice to do it, you have to do it. And what is that point? Where does it come? So, you know, a universal non-volatile memory means that you've got to rethink the whole compute and storage paradigm. I mean, what if I can replace SRAM with memristors, and I can put enough SRAM, essentially, or I can put enough memory directly on a processor chip that you don't need a DRAM type of equivalent. I mean, how does that change your thinking? You know, what if I can put storage, essentially infinite storage, very, very close to your processor and give you enough bandwidth to be able to swap gigantic amounts of information back and forth with very low power, you know, that you just haven't seen before. I mean, so these are, I think, going to be very, very interesting issues. And here's some stuff that I don't understand at all, but you know, as I say, this is. I mean, I understand that we're in the process of perhaps shaking this whole hierarchy up. Now, how much memristor could we put on a single chip? Well, it turns out that it's almost unlimited. One of the guys in my group, Dmitry Strukov, who's now an assistant professor at UC Santa Barbara, came up with an architecture to enable us to essentially stack multiple crossbar memories made of memristors on top of each other and literally interface to or multiplex and demultiplex with an effectively unlimited number of layers with a very simple and sparse amount of CMOS in one layer. This is a real sort of clever way of getting around Rent's rule. And so one way of thinking about it is it's a four-dimensional address space. I'm not going to go into the details of this, but we've actually just published a paper in Proceedings of the National Academy of Sciences on this. I mean, we thought it was we think that this architecture here is at least as important, maybe even more important than the memristor itself, because at least theoretically, with one layer, with one simple layer of CMOS, we can address as many as 1,000 layers of memristors, and each memristor layer could have as much as a terabit of memory associated with it. So, I mean, we're all of a sudden talking petabits of memory in a square centimeter device. Okay? What can you do with that? Interesting to think about. Other issues, other ideas. Well, it turns out that memristors can also perform logic. There's been this long sort of false statement about how you have to have a NOT, you know, in order to be able to perform logic. So, you know, if you can have a NAND or a NOR, those are complete computing systems. Well, guess what? That's actually false. I mean, everything you learned about logic is probably not correct because you learned it in an electrical engineering course and not in a philosophy course, which is the home of logic. Okay? So what I'm going to show you is that memristors can actually perform universal logic, universal Boolean logic, without having to have a NOT. Not having to have a NAND or a NOR. And then I'm also going to show you some ideas about mimicking nerves. So there's this character named Bertrand Russell. Bertrand Russell actually studied logic extensively in the early 1900s, and at one point in time, what he attempted to do was essentially put all of mathematics on a foundation just based upon logic. And so he and Alfred Whitehead wrote a 4-volume tome in the from 1908 to 1912, they published this tome. I've gotten through about the first 7 pages of this 4-volume set. But that's all I needed, okay? Because within that first 7 pages of Principia Mathematica, Bertrand Russell talks about material implication, which is a Boolean logic function that he named. And it turns out that material implication with just a very simple other operation, false, forms a complete basis for universal computing. And it turns out that memristors naturally implement material implication. And so here is a picture, an SCM picture of the world's smallest processor. It's just a linear line of memristors. Now, admittedly, there's a whole bunch of transistors and other stuff out here that's driving the circuitry, but we won't worry about that for the moment. The primary issue here is just to show that a memristor, or at least two memristors, naturally implement this, what's called material implication function. And so we can do a statement which allows us to replace Q with P implies Q in a system. And here's the truth table. It's sort of a funky looking truth table because unlike NAND and NOR, it's not commutative. All right? And that's actually the secret. Because it's not commutative, you've got this issue of being able to do complete logic without having a NOT, an inversion. So here is just an experimental demonstration of that, where we can do, we can essentially synthesize a NOT operation with essentially three consecutive, two consecutive imps. So with two consecutive imps, I can synthesize a NAND. But it also turns out that one of the guys in my group has written a compiler based on essentially compiling C code using implication logic rather than NAND logic. And interestingly enough, when we play with that, the compiled code that we get is always more condensed. It's always smaller by about a factor of 3 than the compiler gets when it tries to compile stuff down onto a NAND. So this is actually something that Bertrand Russell said back in 1910. He said that the implication was the most efficient of all of the simple logic operations to do compound logic. So here we have an interesting issue that we've got a device which simultaneously has state, and so it can be a memory device, but it can also be a logic device, and it can just go back and forth. You can decide if you want some block of memristors to be memory, or some switching network, or logic. And you can dynamically reconfigure it anytime you want. Now, what's the last computing frontier? Well, can we build a neural computer on a single microchip? Well, guess what? It turns out that memristors, what Leon Chua said in his second paper that he wrote on these things was that the only, at that point in time, physical representation of a memristor that he could think of was a synapse in a brain. So if you think about how synapses work, they are memristors. I mean, you give it a signal, and if you have that signal come in a reinforcing way, the effectively resistance or the connection in a synapse gets better, and if you give it opposite or forgetting pulses, it goes away. Well, that's exactly what a memristor is. And so another project we're working on in my group is we're trying to build a chip which computes synaptically. In other words, a non-Boolean logic analog computer that I'm not going to claim that this thing is going to come anywhere near a biological system, but we do think that on a single roughly square centimeter chip, we can get something like 10 to the 11 synapses, and that is actually about at the level of the recent IBM quote simulation of a cat brain. Using their sort of big blue computer or whatever. So here's something we can put on a single chip that in principle should be able to do a computation at about that scale, not by simulating it, not by simulating neurons and synapses, but by emulating them in a system. And here's a design. Here's the chip we're actually trying to build at some level. So the neurons are actually implemented in CMOS, and the synapses are implemented in memristors. How am I doing? Am I about done? Okay. So there's other things that are going on that are probably going to interfere in interesting constructive ways with memristors as well. One of those things that we're working on in our lab is photonics, and essentially our mantra is that anytime you're going to compute, the computation is going to be done with electrons, but at the nanometer scale. But anytime you want to send information more than, say, 100 microns, you're going to do that using light. And so within our group, we essentially have a 10-year roadmap, which goes from building right now an optical bus that we're using for a backplane in a HP blade system. It's a demo at this level, but we're hoping to have this be commercialized in the not too distant future, all the way out to integrating photonics onto the silicon itself. And anytime a bit leaves a core on a chip, it would leave that core as a pulse of light. So we've studied this in detail, and we think that literally over the next 10 years anyway, the combination of what memristors can do and what the optics can do can probably improve the overall efficiency or the overall computational throughput of a computer system per unit of power put into it by 2 orders of magnitude. So we actually think that over the next 10 years, we're going to get more improvement in our computer systems using this memristor combination with photonics than we think that is going to be available to us through Moore's law and shrinking transistors. So that's why we're banging away on this so hard. So I think there's potential for very interesting discontinuities in memory technologies. All right, we are pretty darn confident that this memristor stuff is going to work, and we are essentially going, we got the pedal to the metal right now in order to try to get this into the marketplace as fast as possible. We know that it's not the only technology out there, and we're not the only company out there. So there's a lot of competitive pressure to get us there. And one of the things that we're looking at is what are other disruptive ideas that can come along. I mean, right now we're just sort of looking at this as a non-volatile memory system, but what other things can people do, and what are other trade-offs that might be very valuable to be able to do? So if you have more questions about the memristor itself, I'm listing here 3 papers that first of all describe the idea itself. Then there's IEEE Spectrum's interpretation of that, and then there was an article that I wrote in the December 8th, 2008 version of IEEE Spectrum, which really gives the full history, at least from my point of view. And with that, I thank you very much for your attention.
Thanks.